All right, so it's just basically to show a bunch of examples of the tools that you have to prepare your or design your project. So the exposure time calculator. So I know some people on the call are experts already with that, but some other people might not. And so the way the exposure time calculator is done for Coronagraphy, and that's both NIRCam and MIRI, is that you create a scene with usually a central object and usually a faint point source. It doesn't have capability to do disks, but you can basically mimic a disk with an extended source. And so the ATC basically simulates, it's a bit like a WebPSF, but very, so WebPSF, I should say STPSF now, but a very ideal version of STPSF simulation, because the star is perfectly centered behind the mask. There's no target acquisition error. And since there is no error, it's exactly centered the same for your star and your reference star. So as a result, when you subtract, and so you have basically those strategies in the ATC. And I recommend when you design your APT file, basically you want to know the readout mode you want to use and whether you saturate, or basically the two key things here are maximum fraction of saturation. And I recommend to basically stay below 0.5 or, stay below 1, so that you don't saturate, at least you don't have full saturation in your scene, because that can be a problem for centering, it can be a problem for scaling. So I don't recommend it. Also for the target acquisition, ETC calculation, make sure you have something significant here, but not close to 1. And then when you use the unsubtracted signed scenes or PSF subtraction source only, then you can really see the illumination of your scene. Because if you use a PSF subtraction version, option, sorry, basically the warnings you get with the number of pixels that saturate, they can be for either the star of interest or your reference star. So it's hard to disentangle, and it can be very convenient to use a brighter reference star, for example, to optimize your total time. And so I recommend to basically break down things and use those things. Also, you have to do each channel short and long one by one for NIRCam. This is the Coronagraph visibility tool, and I'm happy to do a demo. It's not installed in the platform because it's a GUI and we don't support GUIs on that platform. It's quite easy to install. It's just a pip install. But basically what it does, basically if you use the NIRCam round mask, you don't need it, or the Leo mask on MIRI, you don't need it. It's really made for coronagraphs that have a non-central symmetric geometry. So for instance, the bar mask for NIRCam, also the 4-quadrant phase mask for MIRI, because you don't want your off-axis companion to basically be behind one of those crosses for MIRI or the bar for the coronagraph. So basically you can introduce a position angle. You can see when your target is observable. So it's also acting as a, so if it were in the continuous viewing zone, for example, this would be continuous. And then the width here, and you can zoom with this button basically, but the width here is how much roll angle you can get with a maximum of 14 usually. But that's basically the how much you can roll the observatory if you want to do rolls. And then for instance, in this case, imagine the red companion here is what you want to observe. It's better to observe here than here when it's actually, closer to the plane of the bar. And so you would basically select this, look at the day of the year and and the aperture PA, and that aperture PA can go in your APT to design and putting an aperture PA is equivalent to introducing a time constraint. So there are two ways to do it then in APT if you want to only observe during that time of the year, for example. This is also old stuff from Marshall Perrin, but basically ST-PSF, you know, basically the wavefront changes with time a little bit, even though, you know, the telescope wavefront is measured every couple of days. I think it's going to change to every 4 days now. But basically the wavefront and telescope team, they are able to always guarantee a good wavefront, but for coronagraphy, you know, it matters. And so ST-PSF allows you, and I don't have the screen capture here, I can add it later. ST-PSF allows you to know for a given star that you observed when the wavefront was the closest to your wavefront, basically your wavefront realization. And that's very powerful if you want to select the reference stars and you don't have a dedicated reference star for your program and you want to look for other ones. Usually it's the ones that are closest in time, but sometimes, you know, telescope can go to similar realization of the wavefront. The reference star selection is very important. I would say especially for NIRCam, because at shorter wavelengths, the spectral type matters more, and so the color of the star matters a little bit more. So you can use different tools. We don't have like a tool that gives you the perfect reference star for your program. So the best is when you use a reference star that has been observed before with high contrast imaging, whether it's in space or with AO or interferometry on the ground, so that you know there's no companion. It's not a binary. And unlike for like future coronagraphs like HWO or Roman, we're not limited by the stellar diameter, at least at those contrasts, but we're limited by the spectral type and also the distance from reference star to your star of interest. This is in JDocs. So I'm not going to stay too long, but those are simulations done with BinRC, which is another alternative to DETC with way more knobs, developed by Jaron Leisenring. So this basically tells you your loss of contrast in this filter, for example, with this mask, if your spectral type is different between your science target and your reference star. And usually it's not that, it's actually quite bad at short wavelengths. It's not as bad as long wavelengths, but then some people go as far as looking at emission lines through in the bandpass of the filter. Also, you know, it takes longer to slew further away, as you know, but this is not a linear relationship. So it basically takes almost the same, about 10 to the 4, sorry, about 1,000 seconds basically to slew 3 degrees, then slew, let's say, a few more. But then it takes a bit less time to slew, let's say, 1 degree. So it's better that your reference star is closer for time, but also for the wavefront and the thermal state of the telescope, basically. So we don't really have on-sky analysis of that. The wavefront team might have a little bit more, but with coronagraphy, this is something to do, actually, to check how much it matters, whether you're at 5 degrees, 10 degrees, 2 degrees, or 20 degrees. I think globally, we care more about the wavefront realization. And I guess it's not a simple relationship whether the wavefront realization stays the same or it's just the background for MIRI that changes, etc. To search for reference stars, you can use SIMBAD, as you know, most of you know, and look for distance. But you can also use the Mariotti Center in Grenoble. It's a center for interferometry, so they have basically catalogs with stars that are pretty safe to use, I would say. I selected my stars for commissioning with that, and I didn't have any problem. And so basically you can classify by magnitude and distance and spectral type. And they also have a page to check if a calibrator that you're thinking of using is bad, because like interferometer users actually keep updating this. But I would say there's nothing like a high contrast image. Then you can check the distance of your star. Then I'm switching to these example notebooks that have been published. This is independent from spaceKLIP. This is really if you want to learn how to run the pipeline yourself for any modes. And so there are two examples for MIRI Coronagraphy and NIRCam Coronagraphy with very useful things. This is an example on the ERS data running this notebook for NIRCam. So by default, the pipeline does not do a super good job with bad pixels because it's actually trying to subtract the darks. If you just keep the darks and run the pipeline the same, you get much better. And spaceKLIP allows way more fine tuning for this. And what you see here, this kind of odd even effect or ripples, this is due to the fact that we use a Fourier shifting technique to align the frames. And so if you have a bad pixel that looks like a square or something, then you get some kind of like a sync function when you shift it.